morning, everyone. I would like to announce our today's speaker. So I have the honor to introduce Anna Kauch, whom I have known since our undergraduate years. So Anna Kauch works in condensed matter physics and solid-state physics. She did her master thesis at the University of Warsaw, and then also her PhD at the University of Warsaw, working on strongly correlated electrons under the supervision of Krzysztof Byczuk. Then she moved on to her first postdoc in Augsburg, where she worked on correlated bosonic systems with Dieter Volkart and Krzysztof Byczuk as well. She worked on dynamical field theory. Then her next postdoc was in Prague at the Academy of Sciences with Václav Janich, where she worked on classical theory of spin glasses. Then she moved to Vienna and worked as university assistant with Carsten Help on strongly correlated electrons again. And now she's the Elisa Richter Fellow at the Technical University of Vienna, working on numerical efficiency, pushing the numerical efficiency by sparse modeling of multivariate functions, basis representations. And she also got into entanglement and computations of entanglement measures from Wien function methods. Today she will give us a talk about capturing non-local correlations in electronic systems through particle response and parquet equations. So the floor is yours.
Thank you. First of all, thank you very much for the invitation, and I'm quite honored to speak here. I must say, during my studies, I did not come to Center of Theoretical Physics here, so I enjoy now the time. So apart from thanking you for inviting me here, I would also like to thank the PhD students and collaborators, some of whom are here, with whom the work was done. So at the moment I am at Technical University in Vienna, and the work that I will be presenting is also funded by the Austrian Science Fund. I would today talk generally about the quantum field theory methods that are used to capture non-local correlations and in electronic systems, in particular about the response functions that are focused on two-particle physics. And I use a quantum field theory method called parquet equations. And don't worry, in my talk, I plan actually to explain all the concepts that are in this title. So I might have a slow start. Please ask me questions, and I'll be happy if I don't give all the details that I have on the slides on the presentation, but instead I get questions and get some details explained. So correlations is everyday experience. So we have both spatial and temporal correlations. For example, if we have bus at different times of day, we experience different correlations at different times. And we also know from experience that the correlations depend very much on dimension. In systems that are one-dimensional, correlations are particularly strong. And of course, at Prague Christmas markets, in 2 dimensions, the correlations are also extremely strong. However, the density is not so important, because also at a football game, the correlations between players, maybe not particularly yesterday, but usually are quite high. Of course, I'm not interested in correlations between people. I'm interested in correlations between electrons, concretely, and solid-state systems. And strong temporal and spatial correlations of electrons lead to many spectacular phenomena, like transitions that lead to changes of resistivity by orders of magnitude from a mode insulator to a metal. And we also have bridge phase diagrams that connected to high temperature superconductors that have magnetic phases, but also superconducting phase. Here, the local electronic correlations play the biggest role. Here, also non-local correlations. And we also have a plethora of systems where these correlations play significant or less significant role, but are anyway important. So in my talk, I will first introduce the language, what are one-particle, two-particle correlations, and what I understand under the term of vertex corrections. Then I will talk about computational methods and what we can get with some computations in terms of response functions. So what can we see in experiments? And I will talk at the end about challenges and solutions, and the reason topic that I'm interested in how to make computations more efficient by dimensional reduction. So the language I speak is the language of Feynman diagrams of Green's functions, response functions. And the response function, the one particle response, is where is easiest to somehow visualize if we have a solid state system that has a valence band and a conduction band and an energy gap between them. So the electrons are fermions, so they fill all the states that are below so-called Fermi energy. And in this particular example, the Fermi energy would lie somewhere between those two bands. And if we do an experiment and we shine light on the system, we can kick out an electron. And what stays is an effective excitation, which we call a hole. It's represented by a Feynman diagram like that. The hole has energy and momentum. Often this index is a multi-index K, but it means momentum and energy. Here, energy with this axis and momentum is this axis. We can have also a different experiment that we actually add electrons to the system, and these electrons can only occupy empty states, which are in the conduction band. And they, of course, at some point will go back to the valence band, emitting some photon, and the photon can be detected, and this experiment goes under the name inverse condition. It's quite interesting because in my calculations, I can calculate one Feynman diagram, one line. And this is actually a response function that is directly measurable in experiment, imaginary part of that Green's function, known as the spectral function. And the experiment is exactly the angle result for the emission spectroscopy. And here we have a source of photons, and in this particular experiment, it was sort of X-rays, and the photons come at certain detection happens at a certain angle, and as here the electron is picked out and it's collected by an analyzer which has some range of angles. These angles are translatable into momenta. Here's some very solid state specific way of denoting momenta. This is momentum 0, this is momentum pi 0, this is momentum 0, along some important lines in the Drude zone. And we can like directly relate those two images. With Fermi energy, we have something like a gap. And the system is this gallium arsenide with some manganese doping, and yeah, we can measure such one particle response directly in experiments. It's very rewarding that you can calculate something directly measurable. For two particle excitations, however, the measurement is not so direct. There's this connection between the actual two particle response function and the experiment is a little bit further. But nevertheless, we have also a quantity called optical conductivity, for example, that we can measure excitations that are two particle. What I mean by two particle, I can excite with light, for example, at the same time. I don't kick out the electron, and it just stays in the system but goes to the conduction band. So I just excite. And from my point of view as a solid state physicist, I now have two objects traveling through the system, and the Feynman diagram has a hole and an electron traveling through the system. And this would be a two particle excitations in the sense of two independent objects. However, they can interact with each other with Coulomb interaction. They attract each other, and they form something which is a truly two particle effect, an exciton. It's not anymore representable by the one particle excitations, but you really need to calculate more complicated diagrams to represent this exciton. Why this is important? So first of all, it's many quantities, not only optical conductivity, but also magnetic susceptibility and other susceptibilities that are intrinsically two particle. That means that I cannot really that easily calculate diagrammatically just a bubble of forward particle excitation, but I have to calculate all the diagrams, and the rest of the diagrams one usually calls further expression. Now, in case of that excitonic excitations, two particle excitations. Some experiments on optical conductivity show very sharp peaks that correspond to these excitonic excitations. And if I do a calculation, this is an estimate. I didn't personally do the calculation. The estimates comes from different papers. The one particle gap that would come by doing this bubble calculation for optical conductivity would be much larger, and no accidents would be detected. So these are truly two particle objects. And in the language that I use, they would be called vertex corrections to the two particle bubble. There are also more complicated systems. For example, samarium titanate is an example. We're also from some experiments and theories, it's speculated that the actual one particle graph is significantly larger, and the truly two particle excitations leads to some spectral waves in optical conductivity that's in gap, right? So here is zeros, here these plots are not from zero, here the gap is significantly larger in electron volts, the zeros down here. In samarium titanate, the gap reduction is not so, it's not like here that we have additional peaks that can be assigned to excitons. There's something else going on. And the question is, what is going on? So, and for that, we have to do some calculations, because only when theory comes with experiment, the understanding is best. So how can we calculate vertex correction? So there are numerically exact methods with which we can directly calculate optical conductivity of a system. However, these methods are quite limited. So exact diagonalization is only for small cluster systems, density matrix generalization group, or quantum Monte Carlo. It's all somehow limited, either to one dimension or to relatively small system sizes. Another end is diagrammatic methods, which work in the thermodynamic limits, so infinite system size. However, only simple diagrams can be easily solved. So usually already such an RPA situation with very high momentum resolution becomes quite difficult. And this is too simple as approximation to take only the interaction U and one class of diagrams to represent quite a lot of physics. And yes.
What is high momentum resolution?
What is so the brilliant zone is like from 2 pi in each dimension, and then you have to take enough dense momentum points if you do brilliant zone integration. So that's the moment, what I mean by momentum resolution. Because quantities like
so you cannot use continuous approximation. You have to.
Sure. So I can do integration in continuous space. So I can use some adaptive integration techniques, but they just simply do not converge if I don't allow for enough computational resources. So the convergence in momentum is quite challenging. So what one usually does is one does grids. So one takes finite grids, because then the integrations can be replaced by matrix multiplications, and that is numerically more efficient. And what is established in recent years is something which is called embedded impurity methods, where it's a combination of these two. So first we solve a small system, and usually just one representative multi-orbital atom with a dynamical self-consistent path to it that represents the lattice. This goes under the dynamical mean theory, or density functional theory, where you have some material-based Hamiltonian that you parameterize in order to construct a many-body model that is treated with this impurity solution. So in that sense, it's a combination of exact methods for which we solve this small problem, and then we get these two particle vertices from this impurity. They are then local, and we calculate lattice response functions. In many cases, it works quite well. so that these impurity vertices would just replace the interaction. So in fact, instead of taking one class of diagrams, we take significantly more classes of diagrams.
Excuse me, can I ask very simple
Yes.
and stupid question? Equation look very simple, but probably it depends on the material you are using.
Sure.
So where is this information about the material?
Here. So the equation stays the same, but information about the material sits exactly in that quantity. So in that boundary quantity. So as I said, this is the one particle Green's function. And it has dependence on momentum, frequency, and usually also orbital indices. And this is the information where the material, the dispersion relation of the material and everything sits in these lines. So this is the material information. The material information will sit also in that quantity, in the Coulomb interaction, because that's what one has to extract. So I do not directly work with materials. I work with models. In order to construct a model, I have to do material calculations. So I don't do it, but people do material calculations that allow us to get the Green's function or some approximation for the Green's function that corresponds to a given material and the value of the Coulomb interaction for a given material. So the materials sit in these quantities. However, in order to calculate some two-particle response, some diagrammatic expansions are needed. This is just a simple one. There are more complicated. Now, I would like to make a link.
Oh, excuse me, there's a question from the audience. So maybe let's
Yes.
try to. Excuse me, Professor, could you please type in the question into the chat? Maybe go on and once the chat.
I always come back to the slide. So yes. So once again, to make the connection with maybe quantum mechanics as it is taught in the physics course and also and the quantum field theory, one can always calculate if one has an exact solution of a Hamiltonian or a spectrum of the Hamiltonian, the Green's function, or any correlation function by evaluating some expectation value of some operators acting on states. So this is a trace of all the states with some thermal Boltzmann factors of operators that create an annihilated particle. That would be the one particle Green's function. So once we have an exact spectrum of the Hamiltonian for a simple system, we can always calculate the correlation functions. The problem is that usually we don't have it. We just have some approximation for the correlation function, for the one particle correlation function. This is an easier one to approximate, and this is the one that we can put material properties in it. For example, a metal insulator, how big is a gap, and everything in connected with one particle physics can be put into that Green's function that can be confirmed by some experiments. And now we would like to go further and from that Green's function figure out further properties of the system, for example, magnetic properties, magnetic susceptibility, or this optical conductivity. And in order to do that, we need that vertex. And either we obtain that vertex also with some other methods, or we try to get this vertex in a different way, diagrammatic way. So this is a two-particle vertex is nothing else as a multivariate function that depends on properties of so these would be the orbital indices or spins, three momenta, three frequencies, so just a very large function. In the sense of diagrams, like the lowest order diagram is just the interaction with two Green's function lines. The Green's function lines are only here for in order to count diagrams correctly, numbered lines. The vertex itself is just the interaction here. That would be the lowest order diagram. These are second order diagrams. There are three of them. Then there are third order diagrams. There are fourth order diagrams, and so on.
What is small parameter?
Exactly. Now, the solid state physics has this enormous problem of not having a small parameter. If we had a small parameter, sometimes it works. Sometimes you can really do this expansion and fine. But normally we don't. So what we do tricks. We classify these diagrams into classes and try to sum infinite number of diagrams with them. So the classes that I classify the diagrams are two-particle reducibility classes. So these third order and fourth order diagrams, if I take more of them. They will also be divisible into classes. In class of two particle Hall reducibility, when I can cut these diagrams in two by cutting these two lines. Particle Hall transversal, if I take these lines, and particle, it's different from particle Hall because the arrows are pointing the same direction.
Excuse me. Oh, pardon.
Sir, I think there is already the question from Professor Bielinski.
Okay. Yes, the next one.
Could you please answer it?
Right.
So the question is about the
Hamiltonian. Yes, the blackboard.
To define the final.
We only have one.
I'm sorry, but we can't hear you very well.
This is the Hubbard. The Hamiltonian would be, for example, the Hamiltonian of the Hubbard model, or some tight binding Hamiltonian, where the electrons, where they are hopping parts of the Hamiltonian of this representing the creation annihilation of electrons on lattice sites, with some interaction, local or non-local. This is a Hamiltonian on the lattice. So these diagrams, they work for many Hamiltonians. They're not limited to one particular Hamiltonian. We have two particle interaction and one particle kinetic part of the Hamiltonian. Now, the propagators themselves, the Green's functions, they represent, I could also not specify them because in that particular formalism, they calculated self-consistently, but they usually contain the information of the dispersion relation of the non-interacting part, so which is just the free dispersion relation of electrons on a lattice. And then they will also have a self-energy that contains the effects of the two-particle interaction. The self-energy can be related, as I will show in a minute, to that particular vertex that I'm calculating, and the entire procedure can be done self-consistently. This is a framework that works independently on what kind of Hamiltonian I have, provided that it has only two particle interactions. Higher, if there would be a three particle interaction, that the formalism breaks down. It's a two particle interaction formalism. And I of course assume some symmetries of the Hamiltonian, for example, the particle conservation. For superconductivity, these diagrams look a little bit more complicated. Okay, I hope.
Sorry, I think there was another question.
Yes, there is some specific picture in your diagram technique with respect to ordinary metal when there is no the gap in the spectrum. You consider some specific material when you have the gap in the electronic spectrum, yes or no?
So this formalism works for gapped and not gapped system as well. You don't have to have a gap in the system. Actually, my actual calculations with this formalism are only for metals. I have a one band insulator calculation for mod insulators where the gap is the consequence of a strong interaction, and we have very few calculations. So and actually they're not mine. So I actually focus on strongly correlated metals, although the picture of the optical conductivity or excitations is easier to show when there is a gap. But in metals, these excitations work as well. They're just not so prominent in experiments.
That's why your technique is applied to conductivity of ordinary metal. Yes?
Yes.
Yes.
I actually will show results for conductivity of ordinary metal. But as I said, the formalism itself is not limited because for some for important reasons, because I don't do the perturbation theory really. I sum these diagrams. I sum infinite classes of diagrams. So if I know that these diagrams are reducible in some way, I can represent each of them as a product of a irreducible and reducible part with irreducible and full connected with these lines in the particle hole, transversal and particle channel. And I have a diagram, a class of diagrams that are not representable in this. And it turns out that I can use the fact that the full vertex is divisible in these classes, that these classes themselves are represented by Bethe-Salpeter equations in order to do some round-robin calculation, together with Schwinger-Dyson equation, which comes from equation of motion for the Green's functions, that I can also have a Dyson equation for the line that includes the self-energy, and the self-energy would be given by the F. So here is the place where my material comes in this dashed line. This is the G0 that contains all the information about the original tight binding model that was constructed based on material. So it looks simple where the material comes in, but it actually depends very much on what this dashed line is, how the calculation converges, for which systems it's relevant, for which it's easier to do it, for which it's more difficult to do it. There is another thing. We don't have a recipe how to obtain the fully reducible vertex. The good thing is that it is at least of order of the interaction to the fourth power, and it has a high level of complication in terms of number of the Green's functions, because it's irreducible. And this is the part that is obtained usually by these exact methods, by some impurity. This is the part that has to be relatively strongly approximated. However, then, once one has this part and they don't interact with this function, one can get this scheme together and calculate the two-particle vertices and calculate the two-particle response functions for a given system. Now, another additional advantage of such diagrammatic approach to the response is that one can use this classification in a sense a posteriori. So once I have done all my calculations, I have as an output actually the response function, the current correlation function that is in the optical conductivity, divided into contributions from different diagrams. There would be the bubble, that would be the particle Hall reducible diagrams that contain the excitonic part of the optical conductivity. That would be the particle Hall transversal that contains something which we discovered is the Python excitation contribution to the optical conductivity, and some diagrams that come from the particle-particle or pairing interactions. But in this category, also some kind of weak localization mechanisms would be contained in these kind of diagrams. So I have some way of decomposition that could give me some insight. Why it's useful, I will talk in some minutes, but yeah, there's a nice paper of some of the people from here, then from Vienna, Alessandro Toschi and Thomas Schäfer, why the decompositions into such classes of diagrams sometimes are interesting for actual electronic systems. What can they tell us about these systems? So I did a calculation for the Havard model. I am very, very sorry I didn't include the Hamiltonian of the Havard model. Here, the calculations are done for the optical conductivity. Actually, here is the optical conductivity. Here is the current correlation function. The vertex correction divided in all those contributions in the lower line. And in the upper line, we just have for different temperatures from the parquet equations method for a very small momentum resolution. The light blue line would be just the bubble contribution. That is the metal, so the optical conductivity is finite at 0, and the shape here is something which is called Drude peak. And we see that there is a suppression of the conductivity at low frequencies exactly by the vertex correction. So the dark line is with the vertex correction. Once we do the decomposition, we know that these diagrams, this transversal particle Hall diagrams, for this Havard model on square lattice, have the biggest contribution to the optical conductivity.
How do we see that
In
the
here,
conductivity is suppressed?
so the blue line is just the bubble calculation, and the dark blue line is the full. So the full is smaller than the in this sense.
Yeah, but I would not say that this is suppressed.
In the sense,
It is just corrected.
correct. Yeah, sure. So in this particular calculation, it's just slightly smaller. Okay, so the question is, so we figured out from the calculation that these type of diagrams that connect a particle Hall excitation with another particle Hall excitations through fluctuations that are concentrated about a particular momentum of phi pi, this is a two-dimensional system, which is connected with antiferromagnetic fluctuations in these systems, that these kind of corrections are important. Now, we wanted to check if they are important for material, but this is at the moment really a no-go. Why? Because the full calculation which we did was just for a one orbital model with poor momentum resolution and a metal. In order to do it for a correlated multi-orbital insulator with enough momentum resolution at low temperatures to check if these vertex corrections have the same temperature behavior or the same character as the ones in samarium titanate, is at the moment not possible. Why? Because if we look at these multivariate functions that are vertices, and we take, for example, 80 frequencies, which enough, so so this is a resolution in the energy dimension, and the resolution of the momentum, for example, just 56 times 56 momentum sizes. This is just an example that my student chose to show the size. Then that vertex already for one orbital has, in principle, 240 petabytes. Of course, these calculations that I was showing were not doing 240 petabytes, basically because the momentum resolution was low, the frequency resolution was low, and I used absolutely all symmetries I could. So I reduced everything to the irreducible Brion zone and whatever, cut out with a lot of effort. You can still reduce some momentum dependence by introducing some form factors, so some combinations of different basis functions for momenta. You can reduce some frequency range, you can do whatever. But these methods, they reduce the computational effort and sizes of vertices only slightly. So there is some need for modeling of these vertices and to really dimensionally reduce them.
Excuse me, where does this huge number of 440 petabytes come from? Because 80 frequencies.
Well, you have 80 here, 80 here, 80 here.
I see. It's the fact that there's just a lot of indices per each function.
It's just a lot of indices, and then you have for this is for one orbital, but you still have like 4 spin indices. Fortunately, with SU2 symmetry, you don't have like 4 to the power of 2 combinations, but you only have like 6 independent, and with a little bit more effort, you can reduce it to 3 independent. It's a lot of playing around, but this is just comes from the fact that this is a multivariate function. So let me talk now about this interpretation of diagrams. So we have had this classification of diagrams, and I said that from our preliminary calculation, these kinds of diagrams are influencing the optical conductivity the most in the parameter regime where we were calculating. So this information could be used like a posteriori to construct some approximative scheme in order to do enough momentum resolution, to do better calculations with that particular one type of diagrams. So that's what we also did and checked how this influence. So this influences optical conductivity. So here we just took a model system in which we have a Drude. So in one dimension, if we take just the linear chain with a local interaction, if we are half filling the interaction opens a gap, so it's a gap system, but with this slightly doped, it can have a Drude. It can be a metal. So we just took a metallic function. We constructed these diagrams and looked at the influence how they have on the optical conductivity. And it turned out that they suppressed it. So in this second line, it's a 2-dimensional system, and the suppression looks like from the full packet equations. It's just the bubble is just slightly larger than the full optical conductivity. So the vertex is negative, it's making it smaller. But for 1D, we actually see that it is as if the peak at 0 shifted to a finite frequency. So we have a model, we have some preliminary results from diagrammatic calculations. What is the application? What materials show such behavior for which this model could be relevant? So it turns out that displaced through the peak so-called, is absolutely ubiquitous in experiments. So it basically it's a suppression of or lowering of optical conductivity at zero, sometimes by losing spectral weight, sometimes but it's a shift when the spectral weight is not. What we observed is without loss of spectral weight. But the shift is observed in really many different materials, and it has many identified physical origins. Weak localization, phonons, charge fluctuations, disorder. What we have, however, in our system is none of that. So we don't have disorder. This is a purely electronic system. We don't have phonons. We don't have really charge fluctuations because we have reduced so the charge fluctuations are not strong because we've reduced the interaction basically to being local, whereas if we have a larger range interaction, the charge fluctuations are stronger. So in our case, the origin of this displaced Drude peak is purely electronic. But the behavior is actually similar to all those systems. With temperature, at high temperature, there's a larger displacement. When the temperature becomes lower, it goes like that. So in experiments, for example, for some organic quasi 1D system, it looks like that. That with lowering the temperature, the peak shifts to lower frequencies. And if we look at the dependence of the position of the peak with temperature, it's so we have a plethora of different experiments done on cuprates, or superconductors actually in some parent compound states, on organic materials, on transition metal oxides, on these are cargo metals. So a lot of classes of materials that show a shift of the maximum of the conductivity of the optical conductivity to finite frequency, and the dependence with temperature is, well, not unique, but in some sense similar in many materials. Here one can see some differences. So our dependences for the particular model system is similar. It grows with temperature. However, it all depends quite a lot on the details of the system in study. So on the place where the material comes in. So it's very hard to predict the particular temperature. But maybe we'll manage. We need, however, not a model system, but a full calculation from the parquet equations with this huge vertex. So in the last part, I would like to spend a few minutes on how to deal with these really large objects. So in order to make really a connection between these theoretical predictions that were done for insufficient momentum accuracy, insufficient material input, quite a lot of simplifications, but to really treat the material input in full scale. So these vertices, they have always some structures. So here are the vertices for the 2D Hubbard model on square lattice on a 6x6 lattice, so very few momentum points. For selected momentum points, and the dependence is just the value of the function as a function of the frequencies in directions. In two directions at third frequency capped at 0. And in here at some larger value. And we can see that these vertices, they have very prominent structures, which means that I don't need like 40 petabytes. So these vertices were not 40 petabytes. They were like tens of gigabytes. I don't need tens of gigabytes of information if I have such structures, right? So a single cross can be written, I don't know. I just need one bit, probably a few bits to store it, right? To store a single cross. Okay, there's some dependence here, some dependence. It's more complicated than that, but significantly lower information content than these gigabytes of that. So if you just take the images and do JPEG compression, you get nice compression. The problem is that with JPEG compressed data, or in similar technique, you cannot work further. So I was showing some self-consistent equations with matrix multiplications. JPEG doesn't work. So what can work? One direction that we tried is a basis representation. If I construct some product bases like that, I can get these structures for free. So a few first basis functions reproduce me already the crosses and lines. And so I can just build these vertices from these functions with coefficients. So this f or r prime would be coefficients. So I can take such a vertex, fit it with that basis, get these coefficients. Epsilon L would be the control, quite nicely controlled error of that approximation. That's work in progress. It would only capture the frequency dependence of the vertices. It would still not do for the momentum and orbital dependencies. There's already a master thesis of now a PhD student, Samuel Bader, who did a good job in representing the vertices and doing calculations even with momentum resolution, added momentum space, and I hope it will go further. But there's another work which is connected with general representation of multivariate functions that have multi-dependencies that are connected with space and time. Namely, there is a lot of libraries, a lot of tools that are very suited to work with tensors. So one can take a tensor and construct a tensor product, like a matrix product state. In the simplest case, I can just say that my dependence of that function on arguments is just a function of the first argument times a function of the second argument times a function of the third argument. Of course, it's a very, very strong approximation, and that would mean that my tensor has like the bond dimension 1. But I can construct my function as sum of different products of these different tensors, and if I sum over enough bonds, then I actually can get an exact representation. What we do here is we make a tensor of that dependencies of the function by adding additional thing. We not only decompose it into products of functions of the arguments, there would be that, like product this times this times this, but each of the arguments we represent in a binary representation, which means that this first new one would correspond, for example, to the, I don't know, to the smallest scale to do the 0, and the new r to the largest case to do the r. So if you need to go to larger frequencies, of course, it could be also from 2 to the 0 to 2 to the minus r, or from 2 to the minus r to 2 to the r, whichever is needed for the problem. The core is that each corresponds to one scale in the binary sense. So we can regroup these arguments and do something like interleaf representation, where the same scales lie next to each other, and we get some representation of the multivariate function as a very long tensor train. Because if I take now this function and write it as product of small tensors, each of them that is dependent on only one of them, right? And if I take only one of then I get a long tensor train, like here illustrated. Each of these tensors depends on only one of these variables, and these are in fact their matrices, and here is just product of matrices. And now how large these products of matrices must be, how large these matrices are, depends on this bond dimension on this line. How many coefficients I have to take in order to represent this thing faithfully. So this is exactly this bond dimension. I can do the exact transformation, not approximate, and get a bond dimension that increases towards the middle, basically exponentially. This is the logarithmic scale, and then decreases towards the end, and that would be no compression. My vertex is not compressed. I have presented everything exactly. However, for typical vertices that we took for the test case, but it's actually the Hubble atom already has a lot of just an atom that has two states, spin up, spin down, plus local interaction. Already that object has a very complicated structure for vertices, and the tolerance, even if I take quite low tolerance, the bond dimension, the maximum of the bond dimension is quite low. To sum it up, these vertices are in that sense compressible, and this matrix product state or tensor trains representation it's very useful to do computations because there are a lot of libraries that allow for multiplication of such tensors, of manipulating, of doing Fourier transforms in a very fast and efficient way. So this is something that I intensely work now. We already have some preliminary results for the parquet equations in some simpler models, actually more complicated than the Harvard item, for some single impurity Anderson model. And this is work in progress that might allow in future to really represent these vertices for materials faithfully.
Excuse me.
Yes.
Yes.
Yes. So I will actually wanted to end now, just to sum up. So first of all, I wanted to stress that there are some two particle response functions that are visible, that require so-called vertex corrections in experiments. So the prime example is actually the susceptibility, but also the optical conductivity, where only including two particle effects can give us qualitatively correct description of the spectrum, so these excitonic peaks or with some weight shift. And of course, quantitative would be ideal, but already qualitative is only possible with taking some of the vertex corrections. That we discovered that there are some important vertex corrections called Pythons, so that they are important for correlated metals. They're probably very important also for some insulators. We, however, don't have results for insulators yet. And for metals, for correlated metals, it seems that they actually do the same as quite a lot of other phenomena on the optical conductivity, which is a bit maybe difficult then to distinguish them from others. This is work in progress. And another, of course, question is we worked to get this displaced Drude with a very simple approximation for something which was motivated by these parquet equations, hard calculations. And the question is if these simple methods really describe these vertex corrections or if it's just accident that it comes out similar. And of course, in order to get the confirmation, if the simpler methods work and if we have a good understanding, we need to do really involved two-particle calculation, and we need to model the correlation functions by that in some way in order to be able to do the calculations. So at the moment, the computational time scales not with the number of points in energy or momentum scale, that would be the n. Normally it would be n to the fourth power, at least for the calculations. It's the case with the fourth power of so-called bond dimension, which means for some systems it will still be prohibitive, but for other systems it will be not, and only logarithmically in number of grid points, which gives access to better resolutions. So at the end, I would like to thank all the students that I worked with and the collaborators as well, and I'll leave you at the summary.
Thank you very much. So I think we have time for a few questions, either from the audience or from people on.
There's a question from the
Alexander, yeah, please.
Thank you. I want to come back to your displaced Drude peak, because you have a missing weight there. That weight has to be recovered, of course, somewhere else in the spectrum because of the sum rule. What is the underlying physics of that?
Okay, so actually in our calculations, the spectral weight is unchanged or not significantly. It doesn't have to be because the sum rule connects the spectral weights with the kinetic energy. And not only the spectral weight depends on temperature, but also the kinetic energy depends on the temperature. So in our case, the kinetic energy depends very weakly on temperature in the range of temperatures that we looked at. So we actually, in our results, conserve the spectral weight. So there's a negative contribution and a positive contribution, and in our calculations, it actually sums to zero. Whereas this picture is a bit misleading. It's taken from that paper. This is maybe more how it looks like. So the spectral weight is, in some experiments, they actually do claim there's a spectral weight loss, but in most cases, this is just a redistribution.
Okay, thank you.
Yeah. Any more questions? Okay, there is one, check.
So with the quantics tensor trains, are you imposing this cutoff? Or are you just finding that when you compute these matrix product states, they naturally are low rank?
Both. We do both. So we either impose the maximum dimension and find the tolerance that is achieved is with that. And this particular plot, we force the tolerance.
Okay, I see, yes. And then, yes.
So the tolerance was forced and the bond dimension was followed. However, I have calculations for the full parquet scheme. For example, here, this is some error this is a dependence of the error in the maximum one on the bond dimension that was assumed from the beginning.
Right.
So this is a different approach. So we said, oh, this will have this bond dimension, and then we looked at what is the error in comparison to the exact value. So here we have the exact.
See. So, and then are you able to quantify the sort of information you're throwing away? Or
yes, so in this case, the error is what we throw away. It's maximum normal. So we are not able to quantify the error in cases where we don't know the exact solution. So the estimate of the error is based on either SVD, so what is the biggest eigenvalue that we cut off, or in case of TCI, there's some local error. This tensor cross interpolation has some local error measurements, which work in most cases, but they're still work in progress on that. So how to reliably estimate of an error? The problem is that it's all very nice when I can have some exact value and I can just evaluate the Bell-Salpeter equation and get the comparison to the exact value with this compressed vertices. However, in the usual case, I don't know what the exact value is. This is for example, this is the last case. I don't know what the exact solution is. I only can here estimate the error in terms of comparison to the converted quantity.
Okay.
So yeah, so there are ways of estimation. I can increase the bond dimension and check. I can increase the tolerance and check, and that's my only way to do. In any case, it's significantly more controlled than anything I did before, where I had like a cutoff of, I don't know, 20 frequencies, and I couldn't do more. So I have absolutely no feeling what the actual error that I do is.
Yeah, we have still time for one more question. I don't see any. So thank you very much.